This lecture today is going to be about Earth motions. We're going to look at rotation as to why the Earth experiences day and night. We're going to look at how the Earth revolves around the Sun and the axial tilt influence on that orbit as to why Earth experiences seasons. So let's start off with the basics. The Earth is moving. When we look at a rotation, we have to understand that the Earth rotates in what we're going to describe as counterclockwise around an internal axis. This leads to day and night. The side that is facing the Sun is daylight and away from the Sun is nighttime. So here's a simplified explanation of that. And I don't love this graphic here, this jiffy, but it's showing you that this rotation is taking place, that we are taking on the vantage point of the Sun, so we're seeing sunlight, or daytime, excuse me, and therefore the other side of the Earth would be experiencing darkness. So keep that in mind. We have this rotation counterclockwise, and we're now going to look at revolution. The Earth revolves around the Sun. It's an external axis. The Earth is moving around this external axis. Rotation, it's an internal axis. It splits through the Earth. The Sun is an external axis in which the Earth orbits around. So, and also counterclockwise. Because the Earth has an axial tilt of 23.5 degrees. Now notice, the axial tilt is going to be very, very significant here. Notice that the axis here is not vertical. It's 23.5 degrees from what we're going to describe as the ecliptic plane. More to come on that. Different locations of Earth receive different amounts of direct sunlight. So the Earth revolves around the Sun, an external axis. Here we see in this picture here. Seasons are the result of the Earth's revolution along with its axis that is tilted at 23.5 degrees, which is measured from the ecliptic plane. So let's look at that for a second. It's moving in this direction. It's orbiting the axial tilt. I want you to observe the directness of sunlight. When our northern hemisphere is simply angled toward the Sun, it's getting more direct sunlight. We're simply going to experience that as warmer or hotter conditions. So we say it's summer. And therefore, when the northern hemisphere is tilted away from the Sun, the southern hemisphere is experiencing summer. So this would be the northern hemisphere winter. Now, it's important for you to realize that this orbit is what we describe as one calendar year. So we have our summer, our fall, our autumn, our winter, our spring. So different positions are all based on the directness of sunlight and the Earth's position in its orbit. So if we describe what is happening with the Earth itself, we need to look at these lines here. So we need to make sure we realize the equator. We have the equator that is 0 degrees north-south. It's a latitude line. We have the Tropic of Cancer in the northern hemisphere, 23.5 degrees north. And we have the Tropic of Capricorn, 23.5 degrees south. And notice, in this case right here, the northern hemisphere is tilted away. Notice the axial tilt. If it's tilted away, the Sun is most direct over the Tropic of Capricorn. And in the next season, you'll see that it's directly perpendicular to the equator. As we continue going on, we move into the northern hemisphere summer. 23.5 degree Tropic of Cancer, the Sun is directly overhead or perpendicular to the Earth's surface at this position. And then lastly, we have the spring in this case. Or this would be the northern hemisphere fall, actually. Excuse me. I happen to read southern hemisphere. So we have these locations as the Earth orbits. As a result of its orbital position in the axial tilt, we just simply get different directnesses of sunlight that lead to different seasons that we're accustomed to. But as with everything, that comes with a caveat. The Earth's orbital path is an ellipse. It's not a perfect circle. Earth's orbit is elliptical in its shape. It's not a perfect circle. As a result, there are times in our orbit in which we are closer and further from the Sun. When we're closest, it's described as perihelion. This occurs on roughly January 3rd. Notice, we are closest to the Sun in our winter, northern hemisphere winter. And we are furthest from the Sun at a time called, or a position called aphelion, which is roughly the middle of our summer. So that should stand in the face of thinking, well, seasons are based on our proximity to the Sun. When we're closer, it's summer. That's not true. It's not true at all. It has everything to do with directness of sunlight. And because the Earth's elliptical orbit, there are times in which the Earth is closer, and there are times in which the Earth is further. But it's not a distance thing. It's the directness of sunlight. And so therefore, in our summer, northern hemisphere is tilted towards the Sun. And in the winter, northern hemisphere is tilted away. So when we put this all together, the summer in the northern hemisphere, we are actually further, the Earth is further away from the Sun, but the northern hemisphere is tilted towards the sun. And in the winter, we are slightly closer to the sun. Remember, this is an elliptical orbit. It's not a perfect circle. The northern hemisphere is tilted away, so we're receiving less direct sunlight. We call that winter. And more direct sunlight we call summer. So let's look at some Earth-Sun characteristics and relationships. Let's think of some basic ideas here. That the Earth is located on average at 93 million miles. That's 150 million kilometers from the sun. The Earth-Sun distance is referred to as 1 AU, or 1 astronomical unit. This value changes due to Earth's elliptical orbit. At sometimes we're closer, sometimes we're further, and other times we're kind of somewhere in between. But on average, it's 93 million miles, or 150 million kilometers. Quick summary. Seasons are not based upon distance from the sun. Instead, seasons are the result of the directness of sunlight an area receives. This is the result of the axial tilt of 23.5 degrees and relative to where Earth is in its orbit. Energy from sunlight is not spread out evenly over Earth. One hemisphere is always dark. We call nighttime, right? This side is receiving sunlight, this side is nighttime. This is daytime. So nighttime receives no solar radiation at all. On the daylight side, only the point directly under the sun receives full intensity of solar radiation. So if it's directly overhead, it's receiving full heat energy. In other words, these little red squares are the area that the heat energy is being distributed upon. From the equator to the poles, the sun's rays meet Earth at smaller and smaller angles, and the light gets spread over larger and larger surface areas. Those are what these red lines are. And notice the poles, the same amount of sunlight energy that's reaching this area here is spread out over this much area here. It's just a lot cooler because there's lots lower sun angle. This here happens to be, I believe this is looking like an equinox. The red lines indicate the different amount of what we're going to describe as heat density. Whereas here you're going to have a greater heat density. Further away from this equator, it's going to be a lot smaller, or a lot lower heat density because the area is spread out, the heat is spread out over a larger area. So that brings us back to incoming sunlight angle. The incoming angle has everything to do with the amount of heat energy that's distributed over an area. Let's go back over this. The more direct the sunlight angle, right, the more direct, the more power measured in watts an area receives per unit area, which is measured in meters squared. In the picture, closer the sunlight angle is to 90, or directly overhead, receives more energy per unit area. It has a greater value of watts per meter squared. We describe this as insolation. Incoming solar radiation is the term that summarizes this idea. The lower the angle, the less power an area receives. Notice that same amount of sunlight energy is distributed over a much greater area. We can say that the greater the insolation angle, right, the greater the incoming angle, closer to 90, the greater the heat density. So let's apply that thinking to what we would view in different, let's just say, climatic regions. So we associate warm weather to tropical or equatorial locations, right, at the equator. If it's directly overhead, we would say, oh, it's hot and warm and probably palm trees and beaches and warm conditions. But we're really associating sunlight angle, even though we don't necessarily think of it in that term. More direct sunlight leads to greater heat density, and thus higher average temperatures, right? Higher average temperatures throughout the course of the year. Less direct sunlight would lead to lower heat density, and when the sun angle is significantly lower on average, we find the polar latitudes, right? Sometimes the sun doesn't come up at all. So much lower angles, and therefore we're kind of a mid-latitude region, and we just have this angle that is, it's not directly overhead, but it's not at this very low angle. It's kind of somewhere in between. So this is 90 degrees, or perpendicular from the surface. This is at a 45-degree angle, and this is at 30-degree angles. So we think about sunlight properly in that it is delivering heat energy, but we often miss the connection to sunlight angle and heat density. So how would we perceive? Chicagoland is roughly 42 degrees north latitude, so this is close. So if I were to observe the sun in its position as it arcs through the sky, we would describe the highest point as its zenith. So the zenith, you'll find that the highest point in the summer, or in this case the summer solstice, is the highest it's going to be. Notice it's not perpendicular. We're not at 23.5 degrees north. We are north of it. In this case, this graphic is showing 40 degrees north latitude. So As it rises, we have longer daylight hours, and the sun reaches a more direct, a more perpendicular location, so we're getting more direct sunlight. Whereas in the winter, the sun rises later, sets earlier, and the sun goes to a much lower condition, or lower height, a lower zenith. So observe the angle and the arc of the sun. They change. This is based on the Earth's axial tilt and relative position to the sun during its orbit. And then your equinoxes, right, are both our spring and fall. The sun is somewhere in between there. So after we have the summer solstice, every day the sun rises slightly lower, right? It reaches its zenith that is slightly lower than the day before. And then when it passes through and we have our equinox of exactly 12 hours of daylight and darkness, we call that the equinox. It continues going lower and lower until it reaches our winter solstice. And then it begins to rise. Each day it's going to rise to a higher zenith each day, crosses back through your spring equinox, and then reaches the summer solstice once again. So we have this process taking place that we're observing. We're observing how we perceive the sun based on the Earth's rotation and revolution. And as a result of the sun fluctuating, we get all kinds of heat in our troposphere, in our atmosphere in which we live. And the three modes of heat transfer that are always taking place are the following. Radiation. Sunlight is radiation. It's simply energy traveling through from point A to point B, but sunlight doesn't need a medium in which to travel through. So sunlight heating over a distance, with or without a medium, right? We feel the sun 93 million miles away. We feel its warmth. That's because radiation does not need a medium in which to travel through. Yet if you had your hands next to this fire, you could feel it. So radiation can act through a medium, but it doesn't require it. It doesn't mandate that there's a medium. Then you have conduction. Conduction is the heating due to direct contact. So conduction, you could say that this handle is going to warm up because the heat is going to be transferred from molecules that are touching each other. An application of this to the Earth. The ground's heating the atmosphere above it by direct contact with the ground to the air. So conduction, here's a good example. And lastly, convection. Warm air rises as a result of a lower density, or you could say increased buoyancy, than the surrounding cooler air. So as soon as you heat something up, whether we talk a liquid or a gas, hotter material is going to rise, cooler material is going to sink. And these circulation cells that we describe are called convection.